Alright, so yesterday you should have done the front and back sheet of the blue packet, which should have been reviewed for you from Algebra 2. So I would like to highlight a couple of things based off of that. Okay? So, first off, when we have this kind of a function right here, I look at the b value, and that b value is going to tell me if it's a growth or if it's a decay. The main thing to remember is that if that b value is greater than 1, it's going to grow. And by grow, what I mean by that is it is going to get farther and farther away from its asymptote. Okay? So that is a growth function. Okay? This also is a growth function. Okay? As you work to the right, if your function gets farther away from your asymptote, it is a growth function. Okay? So both of those are growth functions. A decay function, then, as you get farther to the right, bigger x values, if you will, it's going to get closer and closer and closer to your asymptote. Okay? So a decay function would have a b value somewhere in between 0 and 1. In this general form, a times b to the x power, b cannot be 0, b cannot be 1, and b cannot be negative. Okay? Because those don't make it work. Okay? They don't make functions. Okay? Well, two of them make functions. One of them just keeps flippity flopping, and it's weird. Okay? So we have that. Okay? When we graph exponential functions, we only really graph with two key points. And we look to the exponent. We want the exponent to be equal to 0, or we want the exponent to be equal to 1, because those are nice values. If I can get that exponent equal to 0, anything to the 0 power is 1, so then it would go through the point 0, comma a, or whatever, comma a. Okay? If I can get it equal to 1, then it can go through, then I just have to multiply a times b, and it goes through that point. Okay? So it's nice if we can get our exponents equal to 1 and equal to 0. Okay? Now, continuing on that theme, if the graphs are in the form of that point, or of that function, then the y-intercept of those will always be at 0, comma a. Because if I put 0 into my function, that's going to give me my y-intercept. B to the 0 power is positive 1. 1 times a is a. Okay? And the other thing, the horizontal asymptote is always going to be the line y equals 0, if it's in that a times b to the x form. Most of the time, it's not in that form. Most of the time, it's in the form y equals a times b to the x minus c plus d form. and there's some horizontal shifts, some vertical shifts, some stretching, some all that fun stuff that normally gets associated with a translation of a function. Okay? So first off, let's talk about this d value here. That is going to be my vertical shifts. Okay? That's going to take my entire function and move it up or down. So that is going to affect my y-intercept. That is going to affect my horizontal, oops, that should be an H. I don't know what kind of thing's going on there. That is going to affect my horizontal asymptote. Okay? All of those things are going to get shifted vertically. Okay? The other thing to note is we think normal with the d. Okay? So if it's plus 3 at the end, I'm going to shift my graph up 3. If it's minus 17 at the end, I'm going to shift my graph down 17. Okay? C here is a different kind of a shift. It is my horizontal shift. And here on this one, we think opposite. So if it's minus 3, you should think I'm going to shift my graph 3 to the left, but no, it's thinking oppositely. We're actually shifting it 3 to the right. Okay? A horizontal shift only really will affect the y-intercept in terms of the number that it's going to be, but the process is still the same. Okay? When you plug in 0 for x, that gives you the y-intercept. So really, the horizontal shift doesn't affect anything. Okay? A is going to affect your kind of like how you're growing. Okay? It's going to affect the B, I shouldn't say that. A really doesn't affect, A will stay constant. B more affects your growth. The larger number B is, the faster it's going to grow. So the steeper that growth rate will be. Or the closer that B is to 0, the slower it's going to decay. Okay? So bigger numbers with B make it grow faster. Smaller numbers closer to 0 make it decay slower. Okay? So we have those. Okay? Today we want to talk about E. You discovered E last year in Algebra 2 and its functionality. Okay? So in higher levels of math, base E is primarily used in exponential growth and decay situations. That's how we're going to use it this week. The number E came to importance in the 1600s with Napier and Bernoulli. Okay? So let's graph our function f of x equals e to the x power. Okay? So if I treat this like an a times b to the x type of one, okay, two things come to mind. First, because there's no extra stuff afterwards, my horizontal asymptote stays at y equals 0. So that's where that stays. Okay? Second, I want my exponent to be 0, and I want my exponent to be 1. Okay? So what values are going to be there? Well, that's going to be 0 is going to give me an exponent of 0. So e to the 0 power is what? 1. Anything to the 0 power is 1. So this goes through the point 0, comma 1. An exponent of 1 would be 1, right? Or to get the exponent equal to 1, I'd have to put x equals 1. E to the first power is this number right up there, 2.71828. ... It's irrational. It goes on forever. It never repeats. Okay? So really, it's 2.718281828. And then I think there's some 9s and stuff that come after it, and depending on how far out you go. Okay? So that then, so here would be x equals 1. Here was x equals 0. And then up here, so it would be up here. So this is, does this make sense that this is an exponential growth? Why does it make sense that this is an exponential growth function? John?
So e is your base value, and the base value is greater than 1, meaning it would grow.
Meaning it would grow. Yep, exactly. Okay, yep, my b value is bigger than 1. It's going to be a growth function. Okay? So, but up here, it says that we can use it for growth and decay. But if e is always going to be a growth, how are we ever going to make it decay? Well, let's figure that out. I think that was it on that slide. So if e is a constant, we need to make a decay function out of it. I'll grab my notes here. Okay. So we look at this k number. Okay? So there's this number right in here called k. And that is going to control if it is a growth function or a decay function. Now, in the general form, f of x equals a times b to the x, there were all these funky rules, you know? I mean, we just talked about just 2 of them right now, where if it's a growth function if b is greater than 1, and it's a decay function if b is between 0 and 1, and b can't be 0, and b can't be 1, and b can't be negative, and all those major rules. Okay? Well, in e functions, we don't have that. Okay? In e functions, or in functions base e, in exponential functions base e, I should say, I should speak proper math, it's a growth exponent. It's an exponential growth problem if k is positive. So if k is positive, it is going to grow. Oops, I missed. The bigger that k is, the bigger it's, or the faster it's going to grow. The smaller that k is, as long as k is positive, the slower it will grow, but it will still grow. It's a decay, an exponential decay, if k is negative. then it's going to decay. Again, same thing. It'll decay faster the bigger that k is. It will decay slower I shouldn't say bigger. I should say the closer to 0 it is, it'll decay slower, and it'll decay faster the farther it is from 0.
What if it is 0?
What if it is 0? Good question. So if k is 0, then what's my exponent? No. My exponent is 0. Because if k times x, right? If k is 0, it doesn't matter what x is, it's going to be 0. And so my function will always be equal to 1. So if k is 0, I have a constant function at 1. Okay? So that's neither growth nor decay. So the one condition is k can't be 0. Okay? Good question. So, let's sum all of that up. We are in a growth situation if b is greater than 1 on our standard ones. We're in a growth situation if k is greater than 0. We're in a decay situation if 0 is less than b is less than 1, or if k is less than 0. Okay? I'll give you a couple of seconds to fill that in terms of words. It's good to write things down here to fill those in terms of words. So finish my sentences for me. If my exponential function is of the form f of x equals a times b to the x, then the rate of growth / decay is controlled by the value of b. If b is greater than 1, then the function has exponential growth. And if b is between 0 and 1, then the function has exponential decay. Love it. If my exponential function is of the form f of x equals a times e to the kx power, then the rate of growth decay is controlled by the value of k. If k is positive, I like is positive, less words, then the function has exponential growth. And if k is negative, then the function has exponential decay. Okay? Good stuff. Okay? Now, what I would like to do is I would like to do some exponential graphing with base e. Okay? So, it's going to be a little tricky because e is irrational. Okay? Meaning it's 2.71828 until infinity. Okay? Because it never repeats. Okay? So, I think we can still do it. Okay? Does the rule still apply that we want our exponents to be 0 and 1? Does that still apply? Yeah, that still applies. Okay? So, let's look at example number 1 here. F of x equals 4 times e to the 0.5x. Based off of what we just talked about, is this a growth or is this a decay? Growth, because k is positive. Okay? It might not grow very fast because k is close to 0, but it's still a growth because k is positive. Okay? What value of x is going to make my exponent be 0? 0. 0 is going to make my exponent be 0. So 0.5 times 0 is 0. E to the 0 power is 1 times 14 is 14. Oh, I'm sorry. Should be 4. I'm sorry. I get 14 from right there. Jumped ahead of an example. Okay. Should only be 4. I see through the matrix, you know. Okay. Okay. Alright. So 0, 4, right? Okay. So we go on the y-axis, we go up 4. 1 and 2 and 3 and 4. Okay. What is the horizontal asymptote of this function? Horizontal asymptote of this function. Y equals 0, because there's nothing after the function to shift it vertically. Didn't like you anyways. Okay. Alright. What is going to make my exponent be 1? 2. X equals 2 will make my exponent be 1. Plus? Okay. So 0.5 times 2 is 1. E to the first power is 2.71828, right? What's 2.7? We'll call it 2.7 roughly. What's 2.7 times 4? 10.8. Okay. So I'm going to call this 10.8-ish because we chopped E off to 2.7. Okay. So I'm going to go over 2, 1 and 2, and then I'm going to go up 10. 4, 5, 6, 7, 8, 9, 10, almost 11. So I'm going to be right in there. And my graph then is going to start by my asymptote, come up through my y-intercept, and continue to grow.
Are we only going to need to graph 2 points?
Well, maybe. Okay? And I'll show you the maybe on the next one. Okay? Alright? Everybody good with that? Ideally, yes, because you'll know that it's a growth. You'll know that you get the 2 points, and ideally, it'll work out. Yes, you'd only have to graph 2. Okay? Alright? So, what I would like you to do now is I would like you to try to graph that one. So, first off, where is my horizontal asymptote on this one? It's at 1. Okay? So, I'm going to make that be a little smaller because I can. And so that's going to be, it's going to be up at 1. Okay? Is it a growth or is it a decay? Decay. Why is it a decay? K value is negative. Okay, so it's going to get closer. As I go over here to the right, it's going to get closer to that asymptote value. What x value will make my exponent be 0? 0. 0 is going to make my exponent be 0. Now, that might not always be the case, but in these two examples, it was. Right? There might be, it might be negative 2x plus 3 in there too, and so then you have to, kind of adjust it. Okay? So, negative 2 times 0 is 0. E to the 0 power is 1 times 14. I can say times 14 now. 14 plus 1 is 15. That's way up there. Oops, I should probably write in 15 here. Okay. What value of x is going to make my exponent be 1? Negative 1/2, right? Okay. So negative 1/2 is going to make it be 1. So then I get e to the first power, right? Negative 2 times negative 1/2 is positive 1. E to the first power is 2.7. 2.7 times 14 is what? 37.8. Call it 38. Plus 1 is like 39-ish. Right? So I went half in the negative direction, and I'm way, I can't even get up there. I'm like way up here. Line it up. Okay. Does that really tell me anything? Not really. So this is one of those cases where it might help me to get another point. Okay? So let's try another point. So what do you think? Probably want it to be a positive value, right? Positive 1 or positive 2, 3, 4? What do you want? 2? All right. So let's try positive 2 here. Whoa, whoa, whoa. 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 Let's try positive 2 here. Okay. So if I take positive 2 and I put it in there, I get negative 2 times 2 is negative 4, right? E to the negative 4 power is, usually E is the inverse or the second or the shift of the natural log key. So I get 0.0183. I got to multiply that then by 14, and I got to add 1 to that. And that gives me 1.2564. Okay. So my function is going to come down and make a sharp turn. Okay. All right. That's all I got for you today.